Hello students, welcome to Anne's classes. Let's do chapter 1, Rational and Irrational Numbers, exercise 1A. So rational and irrational numbers. Now before we start the exercise, let's quickly go through what rational numbers are and what irrational numbers are. Now rational numbers are the numbers that can be written in the form of P by Q, where P and Q are both integers and Q is not equal to 0. Any number that can be written in the fraction form, such a way that Q, the denominator, is not equal to 0, are called rational numbers. Let's take some examples. Our first example is 7. Now this number 7 can be written as a fraction. We can write this as 7 over 1. So when we write this as 7 over 1, it is in the fraction form. That means 7 is a rational number. So remember, any number that can be written in the fraction form is a rational number. Another example is 0.9. Now this is a decimal number. I can write this as a fraction. I can write this as 9 over 10. When I convert it to a fraction, it becomes 9 over 10. So 0.9 is also a rational number. Rational numbers include natural numbers, whole numbers, integers, and fractional numbers. So let's look at some natural numbers. Natural numbers are all numbers starting from 1. So here, let me simply take a natural number, say 3. Now I can write this as a fraction, 3 by 1. So it's a rational number now. Let me take whole numbers. Whole numbers are numbers that start from 0. Again, any number 5, I can make it a fraction. 26, I can make it a fraction. So 5 and 26 are all rational numbers. Now what about 0? Now 0 can be written as 0 over 1 or 0 over 2 or 0 over 3 and so on. Here the numerator is 0 and the denominator can be any non-zero integer. Therefore, 0 fits the definition of a rational number because even 0 can be written in the form of a fraction. So natural numbers, whole numbers are all rational numbers. Let's look at some integers. Now, integers, as we know, are a collection of whole numbers and negatives of whole numbers. Now, let's take a few examples to see how we can express integers as rational numbers. Now, if you take 4, now if we have 4, 4 is an integer, we can write it as 4 by 1. Now 0 is also an integer like we just explained earlier. 0 also can be written in the fraction form 0 by 2, 0 by 3, 0 by 4 and so on. Now what if we take a negative integer? Now a negative integer also can be written in the fraction form minus 3 over 1. That means even negative integers are rational numbers. So natural numbers, whole numbers and integers are rational numbers, and fractional numbers are already in the form of fraction, so they also come under rational numbers. Every rational number can be expressed as a terminating decimal, non-terminating decimal and non-terminating recurring decimal. So first let's begin with terminating decimals. Let's take examples. Now look at the first example. Let's divide 1 by 8. So 1 divided by 8. So let's begin the division. So it is 0 here. So we put a point. Now 8 ones are 8 minus, I bring down that 0. 8 twos are 16. 20 minus 16 is 4. I have a 0. I'm going to bring that 0. It's 40. 8 fives are 40. Now our remainder is 0. So in a division like this, where the remainder is 0, the quotient is called a terminating decimal because now it has ended there. This division has ended here. So there are no more numbers to be added to this. So this has ended here. It has stopped here. So it has terminated here. So such a quotient or such a decimal number is called a terminating decimal. Let's work out this example also and see. Let's divide 2 by 5. So 0. I'm going to write 0 here. Now 20, 5 fours are 20. So here also can you see the remainder is 0. The quotient here has stopped, terminated. It doesn't continue, it doesn't go on. There's nothing more to add because we have completed our division. So this decimal is called a terminating decimal. So here our terminating decimal is 0.125, 0.125, and here our terminating decimal is 0.4. So in such numbers where we divide, when the division ends, when the remainder is 0, the quotient is called a terminating decimal. Now we have non-terminating decimals. Here the division will not end. How much ever you continue to divide, how many ever times you divide it, it will still go on. Let's take some examples and understand this. Now we have 3 by 7. Let's divide 3 by 7 and see whether the quotient ends. So 0. So we have a point. 7 fours are 28 minus 30 minus 28 is 2. So we have a 0 here. 7 twos are 14. Again, we continue with the division. 20 minus 14 is 6. We add a 0. We continue, bring that 0. Now we have 60. 7 eights are 56. Minus 60 minus 56 is 4. So we continue with the division. 40. 7 fives are 35. Then again 40 minus 35 is 5. Now this division, as you can see, is going on and on. We don't have a remainder 0. It's going on and on. And here, as you can see, the decimal also is non-terminating. It's not ending. Such decimals are called non-terminating decimals. So here, when we write the quotient for 3 by 7, we write it this way. We say 0.4285, and this goes on and on. So we represent it with the help of dots there. Let's take the next example, 6 divided by 7. So let's divide 6 by 7. 0. So we have 60 here. 7 eights are 56 minus 4. Bring down the 0. 7 fives are 35 minus 5. Again you have your 0. 50. 7 sevens are 49. Minus 50 minus 49 is 1. Bring the 0. 10. 7 ones are 7. Minus 3. Again, as you can see, this division will go on and on. The remainder is not 0. It will go on and on. And such a decimal, the quotient in this case, this decimal is called a non-terminating decimal. So how do we write our answer here? We say 0.8571, and we put dots to show that this division continues. It does not end. So here these two are non-terminating decimals. Now we have the third kind. This is the recurring decimals. Now this is also non-terminating, but what is the difference between non-terminating decimals and recurring decimals? Let's understand with the help of some examples. So here we have 4 by 9. Let's divide 4 by 9 and see. So we have 4. Let's divide this by 9. We'll do the division here since we need more space for this. So divide 4 by 9. So we have 0.4. 9 fours are 36 minus 40 minus 36 is 4. We have a 0 here. So again we have 40. 9 fours are 36. Minus 40 minus 36 is 4. Again we have 40. 9 fours are 36. So as you can see, 40 minus 36 is 4. Now this division is going to continue. Each time we are having the remainder 4, we put a 0, we get 40. Then again we say 9 fours are 36. Again 9 fours are 36. Here also we said 9 fours are 36. This is how it's going to continue. So this is a non-terminating decimal. But what can you see here? Can you see this particular digit 4 is repeating? So such a non-terminating decimal in which a digit, as you can see 4 in this case, repeats continually. This is called a recurring decimal. It's also called a periodic decimal or a circulating decimal. We normally call them recurring decimals, non-terminating recurring decimals. They are non-terminating because it's going to go on, it doesn't end. So it's non-terminating and it's going in a particular pattern a digit is repeated. So this is called a recurring decimal. So let's write our answer here. Our answer here is 0.444. Now this will go on and put the dots to represent. We can also show it this way, 0.4, and put a bar above the 4. So this tells us that 4 is repeated continuously. Now let's do 11 by 30. Let's divide 11 by 30. 11 is smaller, so we put a 0 here. 0.110 we've got. 11.0 we take it as 110. Now 33's are 90 minus 0. 11 minus 9 is 2. 200. Now 30 into 6 is 180 minus 200 minus 180 is 20. So we put a 0. Again we have 200. 30 into 6 is 180 minus 200 minus 180 is 20. Again we put a 0. So we have 200. 30 into 6 is 180. When you subtract, again you get 20. So if you put a 0, again it becomes 200. 36's are 180. As you can see, this is a non-terminating decimal. It goes on and on. I get 200 and 180, 200 and 180, 200 and 180. So it goes on and on. And here can you see our quotient? This is 0.36666. It continues that way. 3 is not repeated, but 6 is repeated. So this is a non-terminating recurring decimal. So let's write our answer here. So this becomes 0.36666. You can continue like that. It goes on. So here terminating decimals are decimals which end where the division ends. The decimal does not continue. As we saw in these two examples, non-terminating decimals are where the quotient, the decimal continues. There's no end to that division. The division goes on and on and on, and the quotient is a non-terminating decimal, as you saw in these two examples. And what are recurring decimals? They are also non-terminating decimals, but the quotient, in the quotient a digit or maybe a group of digits, they follow a particular pattern. They keep repeating continually. Such decimals are called recurring decimals. Now we also have irrational numbers. Now what are irrational numbers? Now the square roots, cube roots, etc. of natural numbers whose exact value cannot be obtained. Those are called irrational numbers. Now suppose I say square root of 4. What is the square root of 4? The square root of 4 is 2. That means for 4, the square root of 4, I have an exact value. So this is a rational number. 4 is a rational number. Square root of 4 is a rational number. But if I take certain other square roots, like the square root of 2, can you see here? The square root of 2 is a non-terminating decimal. So such square roots whose exact value cannot be obtained are called irrational numbers. Let me take another perfect square. Now if I take the square root of 25, what is the square root of 25? 5. So the square root of 25, I can get the exact value. So this is a rational number. Square root of 2, I cannot get an exact value. So this is an irrational number. Another example is square root of 3. See, this is the square root of 3. Again, this is an irrational number because I cannot get the exact value. This will go on and on. So the square roots, cube roots. Similarly, cube roots also, if you don't get the exact value, they are called irrational numbers. Then decimals that are non-terminating and non-recurring are also irrational numbers. We just learned in rational numbers, you have non-terminating and recurring. That means they go in a particular pattern, but they are not ending. They don't end, but they go in a particular pattern. Now, if you have decimals that don't end and there is no pattern at all, then they are called irrational numbers. Examples here, look at this. 2.35638, and it will go on and on and on and on with different numbers. There is no pattern at all. So such a decimal is a non-terminating and non-recurring decimal, and this is an irrational number. Another example is this 1.4142135. Now these are all the answers to the division of certain numbers. This is also the quotient to the division of a particular set of numbers, same way here also. So here can you see these decimals are not ending, so they are non-terminating, but they don't have a pattern, so they are non-recurring. So if they are non-terminating and they are not repeating or non-recurring, they are irrational numbers. Now we have also learned the number pi is 3.141. Now what we do is we normally take it as pi is equal to 3.14, or we say pi is equal to 22 by 7, isn't it? We take the value of pi to be 22 by 7 in all our exercises, in all our working. Now that is just an approximate value. But pi is not exactly equal to 22 by 7. Pi is equal to 3.1415926, and this goes on and on and on. You have many more numbers. They are non-terminating, non-recurring. So that means the number pi is also an irrational number. So what are irrational numbers? The square roots, cube roots, etc. of natural numbers whose exact value cannot be obtained, like the square root of 2, the square root of 3, and decimals that are non-terminating and non-recurring, that is, they don't end and they don't follow a particular pattern, and they are called irrational numbers. And the number pi is also an irrational number. So now let's begin the exercise 1A, which is found on page number 4. Question 1 is the multiple choice type. Choose the correct answer from the options given below. Question A. Let 0 be equal to p by q, where p and q are integers. Now, what additional condition will make 0 is equal to p by q a rational number? So here it says 0 is equal to p by q. 0 is equal to p by q, and here it says p and q are integers. Remember the definition for rational numbers. For a number to be called a rational number, we should be able to express it in the form of a fraction, p by q. Secondly, the denominator q should not be equal to 0. Okay, only then can you call 0 a rational number. Okay, so here let's see the options given to us. Can q be equal to 0? Q be equal to 0? No, q cannot be equal to 0. So here the question is, what additional condition will make this a rational number? This is not the additional condition, so this is not the answer. Now here it says p is not equal to 0. Now p can be 0 as long as q is not 0. So the next one is q is not equal to 0. This is the answer. This is the additional condition that is needed here, so that p 0 is equal to p by q becomes a rational number. Q cannot be equal to 0. Okay, that is a very important condition when you define a rational number. It should be expressed in the form of a fraction, and the fraction's denominator should not be equal to 0. So this is our answer, option 3, Q is not equal to 0. Question B. Every non-terminating decimal number is which of these? Non-terminating decimal number is a decimal number that does not end. It goes on and on and on. When you divide two numbers, if the quotient goes on and on as a decimal number, we call it a non-terminating decimal number. Now that can be a recurring decimal. A non-terminating decimal number can be a recurring decimal. Now what is a recurring decimal? For example, now if I take 1 by 3, if I divide 1 by 3, my quotient goes on as 0.333 and so on, where the 3 repeats infinitely. 3 repeats infinitely. This is a recurring decimal. So a non-terminating decimal can be a recurring decimal. It can also be a non-recurring decimal. And now, what are non-recurring decimals? They are decimal numbers that continue infinitely without repeating a pattern of digits. For example, 1.414235 and so on. Now here what is happening? It's non-terminating, but there is no pattern, so it is called a non-recurring decimal. So a non-terminating decimal can also be a non-recurring decimal. Now, it can also be a circulating decimal. Now, what is a circulating decimal? This is just the same as recurring decimal. This is another name for recurring decimal. So, it can be a recurring decimal, it can be a non-recurring decimal, it can be a circulating decimal. Now, we have to choose the most appropriate answer. Now, in that case, we have to choose option 2, a real number. Real numbers will include all rational and irrational numbers, and non-terminating decimals are real numbers because they also can be rational or irrational. So this answer can be option 1, it can be option 3, it can be option 4, but we have to choose the most suitable one, and that is option 2. Every non-terminating decimal number is a real number. Question C, 7.478478, and you can see the dots here. Now, what is this? Is this a terminating decimal? Now, the dots here very clearly implies that it is a non-terminating decimal, so it cannot be option 1. Option 2 is recurring. Recurring means there is a pattern that is repeating. So here, as you can see, after the point, you can see 478. That same pattern is repeating. So here we have 478 and again 478. So that means this is a recurring decimal. It says it's neither a rational nor terminating, which cannot be true. It's not real. It is a real number. So the answer is option 2. It's recurring because there is a series of numbers that are repeating, and it is non-terminating. Question D, 71 by 75 is it terminating? Is it non-terminating? Is it periodic? Or is it not a rational number? Okay, here we have to divide this and see. Now straight away we can cancel out option 4. Option 4 says it is not a rational number, which is false because it is a rational number. Any number that you can put in the form of a fraction where the denominator is not 0 is a rational number. So it has to be one of these. Now let's divide. To find out the answer, let's divide 71 by 75. So let's do that division by 75. So here it is smaller, so we put a 0 and a point and we carry on. Now 75 into 9. 675, then we subtract, we have 5 here, we have 0, since we have taken 1 there, so that is 10 minus 7, which is 3, and then we carry on again 350. Then we have 4, we can take 4, 75 into 4 is 300, subtract, you have 50. Now this goes on and on. Now here if you continue, it goes on like this. Okay, so this is a non-terminating decimal. This doesn't have an end here, it goes on and on. So this is a non-terminating decimal, so it cannot be option 1. Now it is option 2, which is non-terminating. It is also not a periodic decimal. Now what is a periodic decimal? This is like a recurring decimal where a particular number repeats itself. Now here you can see 6 repeating, but then we have other digits before that, isn't it? So this is not a recurring decimal. It's not a periodic decimal. So the correct answer is 71 by 75 is a non-terminating decimal. Question E, which of the following is terminating? That means ending. Okay, which of the following decimals, fractions here, when you convert it to decimals, will it terminate or will it have a finite number of digits? So that is a terminating decimal. Now, one way that you can find out if these are terminating or not is by actually doing the division, dividing them and then seeing whether the decimal number ends or it goes on and on. If it ends, if it stops at a particular point, then you can say that they are terminating decimals. That is one way. Another way of finding is this. If the denominator, that is these denominators, if the denominator has 2 and 5 as its prime factors, the decimal will be terminating. So this is a shorter way of finding out. Instead of actually doing the division, we take only the denominator, we find the prime factors of the denominator, and if the prime factors are 2 and 5, then we say that that is a terminating decimal. So let's take 13 by 85. Let's take the first one, 13 by 85. Here, let's find the prime factors of only 85, the denominator. Remember, find the prime factors of only the denominator. So 5, let's take 5. 5 ones are 5, and then here we have 3, 35, that is 17. So 5 into 17 is 85. Now here we take 17, which is 1. That means the prime factors of 85 are 5 and 17. So it's not 2 and 5. If it is 2 and 5, then we can say they're terminating. But we have 5, we don't have 2. That means this is not a terminating decimal. 13 by 85 is not a terminating decimal. We can score out option 1. 13 by 85 is not a terminating decimal. Let's take the second one, 9 by 524. So you can do the actual division, or you can just look at the denominator 524, and let's find the prime factors of this. Begin with 2. 2 2s are 4, then we have 12, 2 6 are 12, 2 2s are 4, continue. 2 1s, 2 3s are 6, 2 1s are 2, continue here. Now 131 is a prime number, so we can divide it only by 131 and we get that. That means the prime factors of 524 are 2 and 131. It should be 2 and 5 if it has to be a terminating decimal. That means this 524 doesn't have 2 and 5, it has only 2, doesn't have 5. So option 2, 9 by 524 is also non-terminating. Now let's take the next one. 51 by 405. The denominator is 405. Let's find the prime factors of 405. You can begin with 5. 5 eighths are 40, and then we have 1. Then here the next one is 81. We have 81 here, so we go on to 3. 3 2s are 6, 21. 3 7s are 21. We continue with 3. 3 9s are 27. 3 3s are 9, 3 1s are 3. We don't even have to carry on. When once you know that you don't have 2, you've gone on to another digit other than 2. So this is 3. So the prime factors of 405 are only 3 and 5. It's not 2 and 5. That means option 3 is also not terminating. So we have to answer with option 4, which is none of these. So our answer here is option 4, none of these. Question 2. Are the following statements true or false? And we have to give reasons for our answers. Question 1. Every whole number is a natural number. Now remember, whole numbers start from 0. So we have 0, 1, 2 and so on. And natural numbers are counting numbers which start from 1, 1, 2, 3 and so on. So here it says every whole number is a natural number. No, it's not true. So that statement is false, and the reason is 0 is a whole number and it is not a natural number. Question 2. Every whole number is a rational number. Now this statement is true. Every whole number. Now let's take even 0, starting from 0, 1, 2, 3, all these are whole numbers. And what is a rational number? Any number that can be written in the form of a fraction. So I can write this as a fraction. I can write this also as a fraction. All these can be written as a fraction with denominator 1. So what is a rational number? Any number that can be written as a fraction and the denominator is not 0. So here you can see every whole number here can be a rational number, is a rational number, because we've given it the denominator 1. So this statement is true. Any whole number can be written as a fraction with the denominator 1. Every integer is a rational number. That is also true because every integer can be written in the form of a fraction. So every integer is a rational number because it can be expressed as a fraction with the denominator 1, just like we did here. So you can write it as a fraction. Remember, if you can write it in the form of a fraction, it's a rational number. And every integer can be written in the form of a fraction. Question 4. Every rational number is a whole number. Now this is not true. Whereas the other way it's true. Every whole number is a rational number, but every rational number is not a whole number. Remember, rational number is a number which can be written in the form of a fraction. So if I take 1 by 5, this is a rational number, but this is not a whole number. Okay, so this statement is false. A rational number can be expressed as a fraction, while a whole number is a positive integer or 0. So this is the reason. Remember, we have to give reasons for our answers. Question 3. Arrange negative 5 by 9, 7 by 12, negative 2 by 3 and 11 by 18 in the ascending order of their magnitude. So that's the first thing we need to do. We have to arrange these in the ascending order. Then find the difference between the largest and the smallest of these rational numbers. And finally, this difference, once you find the difference, write it as a decimal fraction correct to one decimal place. So the first thing we're going to do is arrange these in ascending order. Since they're all in the form of fractions, we're going to find the LCM of the denominators 9, 12, 3 and 18. So let's do that. So 9, 12, 3 and 18. Let's get the LCM. You can begin with 3. 3 threes are 9, 3 fours are 12, 3 ones are 3, 6s are 18. Continue with 3, 1, 4, 1 and 2. Now let's go on to 2, 1, 2, 1 and 1. And finally we have 1 each here. So now what is the LCM? LCM is 3 into 3 into 2 into 2. 3 threes are 9. 9 twos are 18, 18 twos are 36. Okay, so now the LCM is 36. Let's use that as the common denominator for all these. So this was 36. This is 36. All will have 36 as the common denominator. Now let's get our numerators. So here we have 9 into 4 is 36. So 5 times 4 is 20 and we have a negative sign there. So negative 20. Next we have 12. 12 threes are 36. So we multiply 7 by 3. 7 threes are 21. Going on to the next one, we have 3 here. 3 into 12 is 36. So we multiply 2 12s. 12 twos are 24. That's negative 24. Then the last one is 18. 18 times 2. 18 times 2, so 11 twos are 22. So we have all our fractions here now. We have to arrange them in ascending order. That means we need to look out for the smallest. So look at the numerators. Since the denominators are all the same, let's look at the numerators. Negative 20, 21, negative 24 and 22. So this will come first because this is the smallest. That is negative 24 over 36. This is the smallest. Then we have the next negative number, which is negative 20 over 36. Then the next smallest number. Now we have positive numerators 21 and 22. So 21 will come first. So that is 21 over 36 and then 22 over 36. Now we have to go back to the main question and arrange these. We've been asked to arrange these, isn't it? So negative 24 is this, which is negative 2 by 3. So let's write that. So that's negative 2 over 3 is smaller than negative 20 is this one, which is negative 5 over 9. Negative 5 over 9, which is smaller than 21 by 36, which is 7 over 12. And the last one, 22 over 36, which is 11 over 18. 11 over 18. So the first thing we have done, that is we have arranged all these in the ascending order from small to big. So now to find the difference between the largest and the smallest, we take this fraction, that is 11 by 18. So that will be, now this is the second part. So 11 by 18 minus negative 2 over 3. So we have to find the LCM, and here we have already done it here, or we can continue by finding the LCM of 18 and 3, which we know is 18. So this will be 18. 11 will remain the same minus, now this is 3. 3 6s are 18. So this changes to 18 and here we multiply by 6. So minus negative 12. So this is minus negative 12. Now the denominators are the same. We can do this. That is 11 minus negative 12 over 18. So this is 11 plus 12 over 18. 11 plus 12 over 18. 11 plus 12 is 23. 23 over 18. Now since this is an improper fraction, we can convert it to a mixed number. 23 divided by 18. Let's do that. 23 divided by 18. 18 ones are 18. And then 23 minus 18. 13 minus 8 is 5. So our improper fraction here is 1, 5 by 18. So 23 by 18 and 1, 5 by 18, which should be our final answer. Now let's go to the third part. It says express this difference as a decimal fraction correct to one decimal place. So let's take 23 by 18. Now we're going to write this as a decimal fraction correct to one decimal place. So let's divide 23 by 18. So 23 divided by 18. 18 ones are 18 minus, here we can subtract this, 13. 13 minus 8 is 5. Now to one decimal place, so we're going to continue with a decimal point. We'll put a 0, bring down the 0. Now 50, 18 twos. 18 twos are 36 minus, now again we need to borrow here. So this is 4 and 10. 10 minus 6 is 4 and 1. So we add one more 0 and continue with our division. It says one decimal place. So let's just check what the other decimal number is going to be after this. Depending on that, we can round it off to just one decimal place. So here we have 140. 18 into 7. That's 126. So let's write that there, 126. So this will go on if we continue with our division. Now here we've got a number with two decimal places. So 1.27, let's write that down. So here 23 by 18, when we divided, we got 1.27. Now we have to round it off to 1.3. Now we have all three answers. We have written in ascending order, that is this answer. Then we have found the difference between the largest and the smallest of these rational numbers, and this difference we have expressed as a decimal fraction correct to one decimal place. That's all for now. See you in the next video.